Alright guys, so this will be our final video for this lab. I know there's been a ton of videos, but I feel like I have to explain a lot of things. So the next step in the lab, the final step, it says use the chi-square analysis to analyze the 10-minute data and sun data. So what exactly is a chi-square? Well, in statistics, there are many different types of tests that you can do for various reasons. The chi-square specifically is used to compare, at the most, usually for chi-square, two different variables and to support or to reject or fail to reject a null hypothesis. So it basically takes a standard or what you expect based on your null hypothesis, compare it to what you actually observe, and get a chi-square statistic. And that chi-square statistic, you will then look at a p-value to compare it to, and you will either reject or fail to reject your null hypothesis. All right, and that is really important, because if you reject your null hypothesis is what you expect will not happen. And your alternative hypothesis, we said way back in another video, is what you expect to happen. All right, so I know these different hypotheses you've never heard of and can kind of get it confusing, but null hypothesis is basically trying to say that the pill bugs are not choosing one side over the other, that they're just moving around at random. All right, and our alternative hypothesis might be that pill bugs prefer the wet side. And that makes sense, because pill bugs need water just like most other animals. All right, so let's get into it. So now for the 10-minute data, we're going to put here what we observed for wet, here what we observed for dry. So for me in my fake data, at 10 minutes for wet, there were 15. For dry, there was 1. Okay, so text box here, 15 and uno. All right. And so then we expect, based on our null hypothesis, if they're not choosing a side and just moving at random, then we expect there to be 8 on one side, 8 on the other. Because otherwise they have no reason to move to another side. But we realistically think that they are moving to another side for a reason. All right, so then we subtract the observed minus the expected. So 15 minus 8 is 7. And then 1 minus 8 is negative 7. Now we get a negative number, but it's going to go away because we're about to square it. And if you remember from math, anytime you square negative numbers, you get a positive number. So 7 times 7, so we get 49 and 49. Okay, and then we take that, what we just figured out, the 49, and divide it by our expected, which is indicated here. So, which was 8. So 49 divided by 8, 6.125. 6.125, and then again, 6.125. All right, and then here it says the next step, add both and place total here. And that's what this symbol means. This is Greek for sigma. The other symbol we looked at that looked like the O was also sigma, but I believe it's just a lowercase sigma. This is an uppercase sigma. But in math, this symbol represents summation, which means add them all up. All right, so add 6.125 plus 6.125. That gives us 12.25. Text box. 12.25. All right, so this is our chi-square statistic. This is our number, our chi-square number. All right, And now we go and find that number for the sum data. So up here we said our sums were 13 and 63. So those are our two observed. So 113 and 63. All right, and we do that math just like we did before. Okay, so I worked through this math and I get from my data 14.20 for my chi-square value. Now the next question is, what do you do with this value and that value that was there but is now not there? What you do is you compare it to these chi-square values and these, to these p-values. So this is a p-value table, something that is very common in statistics. What you're going to need to figure out are degrees of freedom versus to find the p-value that you're looking for. So your notes give you two different looking tables because a lot of times the table that you're given on a test or something will look differently. So just proving a point that it could look different. So, but either way, you'll get the same number. So the number that you will always remember and that you always need to remember when you're doing a chi-square test, you're always going to go with 0.05. So 0.05 and 0.05. A good way to remember that is that, remember, we're dealing with 95% confidence. So that leaves 5% for error. 5% transformed into a decimal is 0.05. So we have 0.05. I'm just going to look at this table here. Now we have, what is our degrees of freedom? Well, think about how many variables are we looking at? We're looking at wet and dry. So we're looking at two different variables. So our degrees of freedom will always be one less of the number of variables that we have. If we had 4 variables, then our degrees of freedom would be 3, because one less. So in this case, our degrees of freedom is 1. So you will go with 1 degrees of freedom versus 0.05. So your number, your critical value, is what these are called. It will be 3.84. So you have 3.84 will be your critical value. Now we're going to come down to our questions here, and it says use the critical value method in chi-square analysis of the 10-minute data to answer the following. What was your calculated chi-square statistic? So you can look back and see what you got for the 10-minute data for your chi-square statistic. That will be the number that is in here. That x2 means chi-square. And how many degrees of freedom are there? Well, we said it would be 1. It says use table 2 to find the appropriate critical value. What is the critical value? All right, we said it's going to be 3.84. We used 0.05 versus 1. You got 3.84. Now, should you reject or fail to reject the null hypothesis and justify your answer? What does this mean about your results? So for that, we're going to need to refer back to the notes. So on page 17 of your notes, it starts talking about hypothesis testing. So we're testing the null hypothesis. Here it explains a null hypothesis is a statement explaining that the underlying factor or variable is independent of the observed phenomenon. There is no causal relationship. In other words, the pill bugs are not, they're just randomly choosing a side. They're not actively choosing a side for any other reason, or it's just chance or error while there's any difference in the means. And so there, the alternative hypothesis is saying that there is difference between the two groups. So that would be that the pill bugs are choosing, let's say, the wet side over the dry side. So that would be your alternative hypothesis. All right. So types of statistical tests. So mainly we have chi-square test and the t-test. Remember, these are commonly seen tests in statistics, if you ever take a statistics class in the future, but they're also used in science. So the chi-square analysis as I said before, makes a comparison between the data collected in an experiment and the data an investigator expected to find. Chi-square test is a way to evaluate the variability that is always present in the real world to get an idea of the difference between the real and expected results due to random chance or if some other factor is involved. All right, so we're going to go down, and I would recommend you guys reading through this, but I'm not going to for the sake of making this video a little bit shorter. All right, here's where it talks about finding the critical value in the form. This is the formula for chi-square. We just worked it out in a data table that made it a whole lot easier to work through. We didn't really have to follow an order of operations because it was set up for us. And this is a practice problem that you should try if this is not making sense to you. All right, and here's practice, more practice. All right, so here it says the chi-square statistic is calculated by finding blah, 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 blah. All right, so in this case, the chi-square is equal to 3.2. And so this talks about how to find the critical value, which we already found. Critical value in this case was also 3.84. Compare the critical value of 3.84 to the chi-square statistic 3.2 that we calculated. So obviously 3.84 is higher than 3.2. If the chi-square statistic, which is this number, the number that you calculated in the data table, is greater than the critical value, which is this number, we will reject the null hypothesis. All right? So then obviously the opposite of that, if the chi-square statistic is lower than the critical value, then we will fail to reject the null hypothesis. So a way to help you remember this is that, remember, you want to reject the null hypothesis because then that means that your data supports your alternative hypothesis, which is really what you care about. So if the chi-square is great, like it's great to me, if it's greater than the critical value, then you get to reject the null hypothesis. That's kind of my way to help me remember it. If the chi-square statistic, the thing that you found on the table, is great, then you get to reject the null hypothesis. However, if the chi-square statistic is lower, then you fail to reject the null hypothesis. And no, that does not mean that you are wrong. In science, you're not really right or wrong. You just collect evidence and you find what you find. And then you move on to do more experiments to find out more. So you don't really fail, even though the word is fail to reject. All right, so we come back over here, the chi-square, or I'm sorry, the critical value. Let me just write critical value right here. Critical value. The critical value is 3.84. My chi-square for 10-minute data was up here. I think at some point I deleted it, but it was 12.25. Okay, so now what? Should we reject or fail to reject the null hypothesis? Well, my chi-square is greater than the critical value, so then I get to reject the null hypothesis. So I get to reject the null reject. All right, and then it says justify your answer. So how do I justify my answer? Well, you can simply say the chi-square value is greater than the critical value. That's it. That's how you justify the fact that you get to reject